Hey students, all right, somebody practicing problems for the test wanted see a solution to number 12, so thought I'd make a solution here for everybody. Starting with this idea, and I'll read it here in a second, but I do want to point out, well, I'll just read it here. It says, an electron is in the nth Bohr orbital of a hydrogen atom. Okay, so a Bohr orbital, remember that we worked this out, and so did your author, that the circumference around 2 pi r has to be an integer number of wavelengths. And so that's kind of the Bohr model. But I thought I would take a moment here to point out that there's also another way of talking about the Bohr model, and that is to say that the angular momentum is quantized in units of h bar, the reduced Planck's constant. And these are actually saying one and the same, and so a couple of people were asking about that, and so I believe Bohr actually did this to be technically correct, but it fits in with this model that the author and I did, and this gives a little bit more understanding of why you have the quantization. Bohr's first attempt, it was just, hey, the angular momentum is quantized, and doesn't really give a reason for it. In fact, you can see that really well if you go 2 pi times r, and you replace the wavelength with the de Broglie wavelength. And so solving this for lambda, let's see, would make h over momentum. And of course, momentum is mv. And so if you move the mv to the other side, you get the mv, and I'll group it with the r, and then I'll get the 2 pi, and that would be n times h. And then if you bring the 2 pi to the other side, you get n times your h over 2 pi, which is the reduced Planck constant. And so this is what I mean by saying these two statements are really one and the same. And so when I did this and your author did this, we're really doing the same thing. This just gives us a little better understanding of the justification of why things are quantized as you get into waves and the constructive and destructive interference. And so I like to start here. And that being said, that might be a good place to do number 11. Somebody was asking about number 11, so maybe I'll do that next, and then use this instead of starting here and kind of go through. But anyways, getting then to number 12, I can read this. It says, an electron is in the nth Bohr orbital of a hydrogen atom. A, show that the period for the electron, so capital T, is equal to some T naught constant times the quantum number cubed. So we've been working with this and have gotten into many quantizations. In fact, I'll just put a few back on here and pull the book down here to kind of show you. Here is the one quantization. This is the angular momentum. So if I put that here, we would have angular momentum is equal to n h bars. That's what we just talked about. He works through and shows other quantizations, because once one thing gets quantized, they all get quantized. And so here he has velocity, although he writes it as velocity squared. I'll just write it as velocity. But he says velocity then would equal to n h bar over mr. And so there would be the equation for the velocity. The radius, and so he's got this one right here, would be n squared h bar squared over, oops, my n kind of looks like an h. Then over an m, and then a Coulomb's constant, and then the charge squared. Probably the most important one is on the next page, where it comes up with the energy being quantized. And so E sub n is negative Coulomb's constant times charge squared over 2 times a Bohr radius, and then 1 over n squared, which was that famous negative 13.6 electron volts for all this stuff, and then the n squared that we've used so much here. And so there's the energy of it. And of course, this problem, I kind of liked it because now something we haven't talked about, it says the time of an orbital would be quantized. It kind of makes sense since their velocity and position is quantized, then how long does it take to go around is going to be quantized. And so once you remember all that, then this is pretty easy to do because you could say something like this: velocity, which would be the circumference to go around, 2 pi r, divided by the period, or rewrite it as period is 2 pi r over the velocity. And so I'll just write the 2 pi and then bring this back in here. So here is the r. So this would be an n squared, h bar squared, over an m Coulomb's constant times the charge squared. Okay, so there's the equation for r. Then if I divide it by velocity, as we did here, we would have an n h bar from that one, and then over an m. And then it looks like another r. And so if you let me then take another r by just saying, okay, this was the quantization for r and square it. Okay, and you'll see the important piece here, right? We've got n squared squared, so that's n to the 4th divided by an n, and there's our n cubed. And so that's what we're asked to show that the period is some constant times the principal quantum number raised to a 3rd power. So we have that. So now, let's see, maybe I'll just put the 2 pi by itself. I've already taken care of that n. Let me go, this would be an h bar to the 4th, and then an m. So that's everything across the top. Then across the bottom, there would be an m squared. There would be a Coulomb's constant squared. There would be a charge to a 4th power, and then another h bar. So I think I got it. There's the n, there's the h bar, there's the e, there's the Coulomb's constant, there's the mass. Okay, there's the 2 pi. I did the n's. There's the h bar in the top. Okay, and then of course a few things cancel off, like one of the m's in the bottom with one at the top. One of the h bars at top cancel off. You could write this h bar as an h over a 2 pi and cancel one of those, but we've got 3 of them. So let me just leave that as a 2 pi h bar cubed in the top, and then my n cubed, and then divide that by the mass and Coulomb's constant squared over the charge of the electron to the 4th power. So that right there would be what we're looking for in the problem T naught, because the problem says show that the period is equal to this, and then it says determine the value of T naught. So I'm going to determine that value. So grabbing my calculator, maybe I'll start with h bar, which I've never memorized it. I've just always gone back to the h, so there's Planck's constant, and then divide by 2 and divide by pi. So there's the reduced Planck's constant. And I'll start there then and say let's raise that to a power of 3. So that's that one. Then multiply by 2 and multiply by pi. Take that and divide it by the mass, 9.11 times 10 to the negative 31. Divide that by Coulomb's constant, 9 times 10 to the 9th squared. Then divide that by the charge of the electron, 1.602 times 10 to the negative 19 raised to a power of 4. And that's everything. And I get, 0. Shoot. When it cubed it, 10 to the minus 34 cubed would get greater than the calculator can handle. That would be greater than 10 to the 10 to the minus 100, which is as big as my calculator can go. Watch. If I went 1 times e to the negative, I'll go 120. It's going to go error. And I bet it can do negative 99. Yeah. But if I divide by 10, yeah, it can't do 1 times 10 to the negative 100. Or it can do it. It calls it a 0. It's out of the range of the calculator. Okay. So with that in mind, let me be a little more strategic in my calculation. Let me get that h bar again, and I said I didn't memorize it, but I just saw what it was. It was 1.055 times 10 to the negative 34. Oops. 1.05 times 10 to the negative 34. Okay, let me just go enter. So there is 1h. I can square it and I'll be okay. But if I do it one more time, I'm going to get 0 with my calculator. So I'll tell you what. Let's start working on this first before we put the other h. So let me go divide by 1.602 times 10 to the negative 19. And let me just do 2 of those and see what I get. Okay, good. Because now I can do one more h, so times 1.05 times 10 to the negative 34, and then also divide that by the other 2 down here, 1.602 times 10 to the negative 19 squared. Okay, so that number should deal with my troublesome numbers. And I'll take that. Let me take it a little bigger, so times 2 times pi, so that's the rest of the numerator. Let me do this one at a time, just to make sure it doesn't even get lower than the calculator. Divided by the mass, 9.11 times 10 to the negative 31. Okay. Oh yeah, that's a small number, so it's going to make it bigger. And then, okay, good. And then divide that by 9 times 10 to the 9th squared. Okay. So 1.48 times 10 to the negative 16 seconds. And then times n cubed. Actually, that was probably a good lesson right there in the operation of a calculator and finite number, especially for those of you who are going into computer science or computational physics. It's, you know, our numbers in the real world, and our calculator has finite numbers, or our computer has finite numbers. So dealing with really big or small numbers, we've got to be a little strategic at times, and it's a whole skill level to do finite numbers. And I guess that's why you computer science people, you've got that class, that finite mathematics class, so that you can kind of deal with this issue. So that being said, you guys are probably better at it than me. Okay, so anyways, I've answered A, and so this is the time then, what they call the T-naught you're looking for. And you would say it would be the time when you're in the first orbital. Okay, looks like I got the hiccups here. All right, so that being said here, let's go on to part B, which says, on average, an electron remains in n equal 2, okay, so n equal 2, for approximately 10 microseconds before it transitions down to the n equal 1, which is the ground state. And that was, of course, an important part of our lesson, and a photon would be released as it went from n equal 2 to n equal 1. Okay. Now, it says here, how many revolutions does an electron make? So if I call n the number of revolutions, I guess I would take, well, how much time, and divide it by the period. So the time is the 10 microseconds. The period, why it's in n equal 2, would be 1.48 times 10 to the negative 16. And then it would be a 2 cubed, which is an 8. And so this would tell me how many revolutions does it make. So 10 times 10 to the negative 6, so 10 microseconds, divided by 1.48 times 10 to the negative 16, and also divided by 8. And so we're looking at about 8.45 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. So it goes around 1 billion times here. Almost 10 billion times. And that's a lot of revolutions. And so I know that in your mind you're thinking, oh, the electron is not in n equal 2 for very long. It's only 10 microseconds. Yeah, but it goes around almost 10 billion times, 8 billion times. Oh, that's a lot. And I think he goes on to ask about an analogy here. See, it says, how many revolutions does this make? And then C, it says, defining the period of one revolution as an electron year, being analogous to the Earth year, motion around the sun. Explain whether you think that the electron in the n equal 2 orbital is living a long life. And I'd say, yeah, it's lived a long life. I mean, it's got a chance to go around 8 billion times. I mean, our Earth is about 4.5 billion years old. So that's about half as much. And so in terms of comparing the electron going around to the Earth going around, the Earth's only gone around half as much as the electron would go around during this 10 microseconds lifetime. So double the age of the Earth, and that would be equivalent to this electron. All right, well, that was kind of a different problem and kind of a fun one. Hope that helped.